in class we were doing some examples of the sum of a geometric sequence. And here's an example of a very short geometric sequence turned into a sum, 2/3, 2/9, 2/27, 2/81. And what we got was an interesting answer that it was almost 1, and the difference was a very simple thing. It was just 1/81. It was 1 minus 1/81, or 80 over 81. And what I want to do is generalize that. Let me first remind you of the definition of a geometric sequence. That's where we have a constant ratio between successive terms. So for example, 2/9 divided by 2/3, when you simplify that, that's 1/3. It's gone down by a factor of 3. And 2/27 over 2/9, that's equal to, again, 1/3. And if you continue this pattern, 2/81, that continues the pattern. If you continue that pattern, if you just list them, that would be a geometric sequence. If I just put commas between these and I said, I'm interested in this sequence of numbers, and just as a function of n, that would be a geometric sequence. But we're interested in not just listing them, but what happens if you add them up? Because we discovered in class the previous day that it seemed to be that kind of sum where we have a bunch of different numbers that are related in a geometric fashion, and we added them up. That would seem to be crucial to the answer, or a simple answer, to our annuity question, where we're paying in money for retirement on a regular basis. So let's see. This is one way to detect it's a geometric sequence, but there's a closed formula. If we, again, we're not summing them up quite yet. If we want to find just the formula for all these terms, the pattern is that they all have a 2 in them, and they all have a 3 to a power. And this is going to work if we start with n equals 1, which we don't have to, but it's a fairly common place to start. That's going to work for this pattern. Now we're going to see that sometimes we're going to have some modifications, like powers to the n minus 1, to make things work out nicely. And another way to write this is a sub n equals 2 times the number 1/3. Oops. That's that common ratio, and then to the nth power. Okay. So that kind of formula is what we're going to have for a geometric sequence. So let me go ahead and deal with the n minus 1 issue right now. The thing with the problem with this is that this 2/3, we want to kind of say that's where we're starting with. That's our home base, 2/3. Now, in this example, because I contrived it to have this really nice property with the 1, it happened to start out with already having an over 3 in it. And that's why when n equals 1, we already have a power of that 1/3. But it's nice sometimes to think of it as saying this guy is where we're starting, and we haven't started putting in the powers yet. So what we could write this as is a sub n equals, I'm just going to take one of those powers of 3 out of the 1/3 of the n, and so that I have exactly the first term. And then I'm going to have, I'm going to have a 1/3, and then it's only going to have n minus 1 powers. That's still going to give you exactly the same formula. It's just another way to write it. And the reason that's useful is that that's the first term times the ratio. This constant ratio is usually called r for ratio, r to the n minus 1. And the book, I think, the book just calls a1 a straight up. And so that's going to be a pretty good master formula. It's not the only possible master formula for the terms of a geometric sequence. That's just how to generate the actual pattern of the numbers. Remember, what we're really more interested in is adding them up. We'll do that in a second. But this is going to be a pretty standard formula for the terms of a geometric sequence. Okay, so what did we notice about the pattern of the sums here? Our more interesting thing is summing these guys up. And what we noticed is if we took 2/3 plus 2/9 plus 2/27 plus dot 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 plus up to 2 over 3 to the n, and we're going to have to think about how if there's that n agreeing with this kind of n, we'll worry about that in a minute. What we got was 1 minus 1 over 3 to the n. That's pretty cool. And let's see if we can adjust that. It's going to be a little weird. It's not going to look quite as cool in a minute here. But I want to write it as 2/3 times 1 plus that 2/3 times 1/3 plus that starting term 2/3 times 1/3 squared. And if I write it that way, always keeping that common factor of 2/3, then it's going to be 1/3, and again to the n minus 1. And so it just is a standard way to write these, with the first term coming out as a common factor. And then you just get powers of the ratio, and the nice thing is you start with 1, the simplest possible power, the 0th power. If you write it that way, then I just rewrote that expression. I didn't change it at all. And so it's still this number. And what we see is there's unfortunately kind of a mismatch. But we'll see in another example why there has to be a mismatch. This goes up to where the power is n minus 1. This has the power being n. And so that is going to be important. I didn't want to put that in the initial examples to kind of emphasize how pretty it is. But there's going to be a little bit of an issue with n minus 1s and n sometimes. Okay. So we want to generalize this. We want to see, is this always something that happens with a geometric series, that there's a shortcut? The amazing thing here is that if I asked you to add up 100 different terms like this, there's a super shortcut. You just have to take 1 minus 1 over 3 to the 100, and you're done. And that's a wonderful thing to be able to do. So let me just show you one more example that we looked at in class, and that is probably the simplest example. The nice thing about the examples we started with, like these fractions, is they always were adding up to, they're getting closer and closer to a fixed number. But the pattern in some ways is clear if I have the simplest starting point, which is 1, so that's going to be the a equals 1, and the ratio is the simplest number that's actually going to do anything interesting, which is 2. And so that's going to be, we figured out that was 63, and we figured out the pattern. If we go up through 2 to the n, well, let's see. Do we want to go through 2 to the n? Let's actually go through 2 to the n minus 1, because that's going to be the nth term. If this is a1 is 2 to the 0, and a2 is 2 to the 1, then a to the n is going to be 2 to the n minus 1. That's just using exactly this formula. 1 times 2 to the n minus 1 is the nth term. Okay. So let's see what that should be. Here, this is the 5th power. And the key thing here was the nice pattern was it was the next power of 2 minus 1. And that's where this next thing comes in. That's the simplest place to see why this n minus 1 can't match with the n. You can't take 32 minus 1 and get 32 plus some positive numbers. This is a power of 2 minus 1, but it's not the power of 2 you ended with. It's the next one. So if you happen to be writing that as n minus 1 already, it's actually kind of nice, because that's going to be 2 to the n minus 1. Okay. So we're getting some nice things. This is looks a little bit different because it looks like it's in a different order. 1 minus something with nth power to the n minus 1. But you still have this idea that you have the next power of the ratio. In fact, let me even rewrite that a little bit with the 1/3 all to the n. That ratio gets raised to the next power, the power you didn't use, and then something about subtraction. Okay, so here's the general argument. So we're going to have a plus ar plus ar squared, and this is going to be very much like in the book, because there's kind of a standard argument here that it's not really worth beating around the bush and doing something more complicated. Plus dot 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 plus ar to the, and we're going to stop at n minus 1, because that would be the 1, 2, 3, 4, the nth term of this sequence. And we want to figure out what that is. Okay. Well, we're going to do something somewhat like what we did, one of the versions of the trick for arithmetic sequences, which is call that s, and then try to play with this expression in a way that takes advantage of the pattern. In the arithmetic sequence example, we flipped the order and wrote it below and added. But here, the pattern is that all these terms differ by a ratio of r. So something about multiplying by r is a really good thing in this sequence. So what we're going to do is we're going to multiply everything by another power of r. ar plus ar squared plus ar cubed plus, what I'm doing is I'm taking all these guys and I'm multiplying them by r. A times r. ar times r is ar squared. Hey, that's funny. That's already showing up in the original. Well, we'll use that in a minute. Ar squared times r is ar cubed plus ar to the fourth plus dot dot dot. Whoops. Plus dot dot dot. Plus, and then it's going to end with ar to the, there's an ar to the n minus 2 hiding in here, so I'm going to put that in. When you multiply that by r, you're going to get ar to the n minus 1. And then it's going to end up with an ar to the n, because this guy times r. Now that's equal to r times s. And it's not syncing up too well. Let me fake it here so it syncs up better. And there's another reason it's not syncing up too well, because when I multiplied all these guys by r, I got an extra one here. Let's just sort of have that be understood in the dot dot dots. Now it's syncing up very well. Now we want to look at these and say, how would we play these off against each other? Well, they have a lot of things that are the same. And if you have two equations with a lot of things that are the same, subtracting them is a really good idea. So I'm going to subtract the bottom from the top. And I'll get a huge amount of cancellations. I get a left alone on the top, but everything in the middle cancels out except for the ar to the n. And I get s minus rs, but that is equal to s times the quantity 1 minus r. So this trick has done the main work here, which is I didn't want to have to sum up all this stuff. But by comparing it to comparing s to rs, I managed to cancel out almost all that repeated summing, and I've just got a couple of things, just some subtractions. And then I can solve for s. So a times the quantity, well, times the fraction, 1 minus r to the n, over 1 minus r is equal to s. And that's a huge, huge shortcut. That this whole huge sum of n different things, a times n different powers of r, can be done just by taking the next power. Notice that's that next power showing up, n instead of n minus 1. Multiplying by a as a common factor, because a was a common factor in the entire calculation. And then dividing by 1 minus r. Let me just show you one example real quick. We had one that was 7 plus 7/3. This was a bit of a mysterious one when we started looking at it. 7 27th plus dot 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 plus, and then 7 over 3 to the, and let's write it, let's fudge a little bit. We now know that it's going to be nice to write that as n minus 1, because this is 7 times 1 over 3 to the 0. And that's starting with what we like, which is no powers of the ratio, and going up to the n minus 1 power of the ratio. So that's just fudging a little bit from the example that we did in class. And what's that going to be? Well, let's just write down. A here is just always the first term. A equals 7. R is 1/3. That's the common ratio, the thing that we're multiplying by each time. And that's it. That's all I have to know. So that's going to be that 7 is a common factor, which we noticed that a 7 was in the whole expression, so the 7 is going to come out as a common factor. And it's going to be 1 minus 1/3 to the nth, and then divided by 1 minus 1/3. We can clean that up a little bit. And what we noticed was there was a 21 halves coming out. Well, that's 1 minus 1/3 is 2/3. When you divide by that, you're going to get a 3 halves. Let me just write it out. 7 times 3 halves, which is 1 over 2/3, times 1 minus 1 over 3 to the n. And that's what we had figured out as our answer for this problem. But this here we can just do it as an instance of using this master formula.